Yes, good evening, everyone. I'm Buinza Samuel, that is group SW, from group SW 18, that is group SWML 18. So I'm talking about the EWS classification system, that is for the model audit, and the AI, the XAI, sorry. So it majorly talks about the comprehensive evaluation of the four models of the waste detection types that I've so far covered. That is for the submissions that I've made. Yes, so when you look at the presentation overview, we have the objective, that is to present the architecture, training, and rigorous evaluation of the four models. That is the ones that have built for the EWS classification with a focus of audibility and explainability. So when we look at the agenda, first of all, you have the system overview and the problem statement. Then we have the feature engineering pipeline, the four models, that is architectures and training. Then we also have the evaluation frameworks and metrics. Then for the model audit and explainable AI, that is XAI, we have the comparative performance analysis, and then the summary and feature work. So when we look at the system overview and problem statement, here we have the goal being the automate waste sorting using image derived features to improve recycling efficiency and waste management. Then we have the dual mode architecture concept, that is a two-stage approach where a binary model first detects an e-waste, then a multiple class model then identifies a specific waste type. So we have the four models audited, that is binary random forest, binary XGBoost, then the binary neural network, then the multi-class XGBoost. Those are the four major models I've been covering. Then when we look at the data set, it's approximately 1,000 synthetic samples across the 9 classes for the e-waste: cardboard, glass, metal, organic paper, plastic, textile, trash, that is generated from the realistic feature distribution. So when we look at the feature engineering pipeline, we'll look at the raw features, that is the aspect ratio, the blur, brightness, contrast, edge, to mention but a few. Then when we come to the derived features, this captures the nonlinear relationships and interactions, where we have aspect ratio squared, brightness, contrast ratio, edge entropy, interaction, and the others as seen. So when we come to the categorical features, that is the resolution category being low, medium, high, very high, one auto-encoded, and giving us the total engineered features as 18 that are used for all the models. Then specifically model 1, that is binary random forest for the e-waste detection. This architecture ensembles 100 decision trees with a bootstrap sampling for training each tree, then a feature randomization at each split. Then when you look at training, it is optimized for binary classification. Evaluation, when we come to evaluation, that is for matrix and XAI preparation. It looks at the high accuracy, precision, recall, and F1 score, that is for the EWS class, used as a baseline for the interpretability. So when we come to model 2, that is for the binary XGBoost for the EWS detection, here we look at the architecture being gradient boosted decision trees with built-in regularization, that is for L1 by L2 on leaf weights, shrinkage, column sampling. Then we have training, sequential, that is majorly sequential tree building, where each new tree corrects errors of the previous one. Then we look at evaluation, that is which often provides high predictive accuracy than the random forest. Then we look at the XAI audit focus, that is multifaceted feature importance analysis using weight, gain, then cover. Those are the three things it mainly covers while doing the importance analysis of these features. So when we come to model 3, this covers the binary neural network, that is the MLP for EOS detection. Its architecture mainly inputs the layer. The input layer covers the 18 features. Then the hidden layer covers the multiple layers with the RE, LU activation. Then output layer is one neuron with a sigmoid activation for binary probability. Then when we look at training, it optimizes DAM. Then the loss is always a binary cross entropy techniques, that is early stopping, where we have 10% validation split to prevent overfitting. Then when you look at the XAI audit focus, that is understanding how input features contribute to the final prediction. That is, yes. So when you come to the fourth model that I did as my last model, that was the multi-class XG boost, that is for the 9-class classification. Its architecture is majorly a multi-class extension of the XG boost. Then it normally gives an output that uses softmax function to output probabilities for the 9 classes. Then the key parameters, they are the N estimators, maximum depth, the learning rate, which is 0.1, the maximum depth is 8, estimator, the N estimator is 150, then the evil matrix, that is for the multi-class log loss. Then when we look at its evaluation, it majorly covers the matrix and the XAI prep, where the confusion matrix analysis is there to identify the commonly confused classes, that is giving an example of organic then versus paper. So we have the XAI audit focus, which is a global feature importance for the local explanations for the specific misclassifications. So we come to so that was briefly about the 4 models that I've covered so far. So when we come to the unified model evaluation framework, here we have a cross-validation strategy, which is a 5-fold cross-validation that is used for all the models to ensure robustness and prevent overfitting on the synthetic data. Then the key performance metrics for the binary models, there is accuracy, precision, recall, F1 score, to mention but a few. Then for the multi-class model, there is accuracy, micro or macro, weighted average, precision, recall, F1 score, confusion matrix analysis. This is essential for understanding the model errors and guiding the feature engineering for the multi-class model. Then we look at the model audit, that is introducing explainable AI. Why do we audit? This is to move beyond the black box predictions and build trust, ensure fairness, and identify model weaknesses. Then the XAI techniques used, we have feature importance, that is global, which features are most influential for each model's decision. Then we have the local explanation, that is for individual predictions. We have the partial dependency plots, how does a change in feature affect the model's prediction on average? That is majorly what it talks about. Then we come to the XAI audit feature importance comparison. That is for the binary models. We have the audit question, that is, do all binary models rely on the same features to detect the waste, to detect e-waste? That is the question before us. Then we have the analysis, that is for the random forest, that might highlight edge density and texture complexity. Then we have the XGBoost, that is for the gain, that might show brightness contrast ratio as the most informative. Then we have the neural network that could reveal complex interactions, that is Iggy, the blur is only important when the entropy is low. Then the key insights is that the different models learn different representations, and the ensemble approach voting, which could leverage their complementary that may leverage their complementary strengths for more robust systems. Then we look at the AI audit, that is for the local explanation. Example scenario is that an item is predicted as e-waste by the binary neural network. So when for the audit question is why? So when we come to the audit, the local explanation, it comes to feature pushing for e-waste, where the file size is put in consideration, the brightness, contrast ratio that is majorly high, then the file size is also high. Then features pushing against the e-waste, we have the aspect ratio, which is close to 1.0, the blur that is always high. Then with that, we have a conclusion that the model learned that waste items, that is for the circuit boards that often have distinct metallic sheen, that is for the high brightness, stroke contrast, and are compared at a high resolution, that is high file size, differentiating them from other waste. So still on the XAI audit, that is for the model misclassification analysis, that is for multi-class. We have the audit question is that why does the multi-class XG both confuse organic and paper? We come to the analysis where we have the confusion matrix with a high misclassification rate between those two classes, then the partial dependency plots where we have for paper and then for organic. Then for the root cause, the systematic data feature ranges from organic and paper made be too similar for certain attributes. Yes, for certain attributes. Then for the comparative performance analysis, here we have for the binary model for the EOS detection, whereby we have the XGBoost likely achieves the highest accuracy due to its boosting nature and visualization, handling synthetic data well. Then the random forest provides strong, robust performance and clear feature importance. Then for the neural network, performance is good, but may be most susceptible to limitations of synthetic data. Then for the multi-class model, here the XGBoost achieves a good overall accuracy, but confusion matrix reveals challenges with visually similar waste categories. The overall best performance is that the ensemble of all the three binary models combined with the multi-class XGBoost would likely be the most robust and accurate system. Then model strength and limitations. Here I'll go through very fast because they're a bit brief and straightforward. We have comprehensive feature engineering that is there to waste properties among the strength. The second being multiple models for comparison and ensemble creation. XAI audit provides transparency and insights for model refinement, clear separation of concerns. Then for the limitations, the Models are trained on synthetic data and may not generalize to real-world images. It requires all the 18 features to be computed from images. Those are the two limitations. Then for the future improvements, integrate deep learning, that is for the CNNs, replace handcrafted features with automatic feature extraction from raw images. That is one feature improvement. Then the real world data collection, that is retrain models on actual waste images. Then deployment, which is package the best performing model, specifically that. Then in summary, the four distinct models, that is for the binary RF, that is random forest, the MLP multiclass, that is XGBoost, were built and audited. Then the XAI techniques were used to audit the models, providing crucial insights into their decision-making process and covering potential weaknesses. Then the key insights: model transparency is not an add-on but critical component for building a reliable, trustworthy, and effective waste classification system. Then lastly, the Act and framework lay a solid foundation for the future work and real-world data and deep learning integration. Thank you very much. By the names of Inza Samuel, that is what I had for you.